When an engineered carbon fiber strut is subjected to immense longitudinal compression, failure is sudden, violent, and complete. To understand why a material with such high tensile strength fails this way under compression, solid mechanics traditionally relies on idealized models. Engineers map the internal composite fibers as perfect periodic arrays, usually arranged in flawless hexagonal or square grids. But physical manufacturing introduces continuous spatial chaos. Real composites do not form perfect grids. This physical chaos produces critical structural defects. Within the cross-section, we find resin-starved regions where fibers clump tightly together, sitting immediately adjacent to resin-rich voids where fibers are entirely absent. In a theoretical, perfectly spaced grid, compressive stress distributes evenly across the entire structure. In reality, physical stress pools heavily around these manufacturing defects. During loading, extreme stress spikes localize precisely at the points of fiber agglomeration. Evaluating a composite based on a uniform grid blinds engineers to these localized stress spikes, causing them to overestimate the structural strength of the material. Simulating an entire composite structure, like an aircraft wing, down to the scale of individual fibers is computationally impossible. The processing power required to calculate that many interactions does not exist. Instead, engineers utilize a representative volume element, or RVE. This is a microscopic bounding box, a highly focused, calculated sample of the material used to extrapolate large-scale physical behavior. Building a valid RVE presents a strict computational dilemma. An algorithm cannot simply randomize fiber locations and expect accurate stress data. The virtual geometry must perfectly mimic the chaotic layout of the actual manufactured material. The mathematical link between a physical scan and a generated RVE is called statistical equivalence. Proving that a generated model is statistically equivalent to the physical material is a required mathematical threshold. Until this equivalence is proven, finite element analysis simulations cannot yield trustworthy failure predictions. Extracting raw data from a physical scan, an algorithm segments the cross-section into a binary mask, isolating every fiber. From this, engineers calculate the foundational fiber volume fraction, measuring the total white area against the black background to determine the fiber-to-matrix ratio. Additional deterministic metrics are extracted simultaneously, establishing the baseline fiber diameter and the average ratio of the gaps between the fibers. However, these basic physical descriptors have a clear limitation. A perfectly spaced theoretical grid and a highly clumped defective physical sample can possess the exact same fiber volume fraction. Volume and baseline geometry cannot account for spatial distribution. Relying solely on these basic descriptors leaves models blind to the highly localized defects that initiate material failure. To map the spatial chaos, we calculate the nearest neighbor distance, or NND. We trace the shortest possible vector from one reference fiber centroid to its absolute closest neighbor. Extracting this for every fiber generates a massive dataset of spatial relationships. We map the frequency of these distances, creating a probability density function. If the normalized mean distance approaches 2, fibers are severely agglomerated, and the curve spikes into a tight high peak. If greater than 2, fibers are dispersed, showing a wide, flattened distribution. The shape of this curve quantifies the manufacturing quality by identifying the specific frequency of clustering throughout the sample. A sharp peak in the PDF curve indicates a high frequency of fibers touching or nearly touching, the precise physical conditions creating structural weak points. By identifying that aggregation peak, engineers can predict the likely magnitude of the interfacial shear stress hotspots found within the material's microstructural clusters. The nearest neighbor distance only evaluates adjacent fibers. To map the wider spatial relationships across the surrounding resin matrix, we require higher-order statistical functions. Ripley's K function measures expected fiber density. An expanding concentric boundary grows outward from a reference fiber, calculating the number of neighbors within an increasing radius. In a theoretical defect-free distribution, the resulting curve smoothly plateaus, saturating at 1. In physical samples, fluctuations in the medium range of this curve expose complex, large-scale clustering. These are high-volume fraction defects, completely invisible to basic distance metrics. We also utilize the two-point correlation function to map specific phase boundaries across the material. This function drops random vectors of varying lengths across the RVE, calculating the exact mathematical probability that a line spans from fiber to matrix, matrix to matrix, or fiber to fiber. Together, these higher-order statistical distributions quantify the spatial chaos of the physical scan. They establish the target baseline for any synthetic reconstruction. With physical targets extracted, optimization algorithms take over, generating synthetic fiber locations from a blank mathematical canvas. The algorithm operates in a continuous iterative loop. It slightly repositions virtual fibers, recalculating the simulated PDF and K-function data until the synthetic curves perfectly overlay the physical targets. The output of this computational loop is a cleanly generated two-dimensional model of random fiber distribution. Compared to the idealized periodic grids used in traditional solid mechanics, this structure exhibits deliberate, mathematically calculated chaos. Because the spatial statistics of this generated volume perfectly align with the microcomputed tomography data of the real material, it functions as a mathematically valid statistical clone, ready for finite element analysis. However, physical composites exist in 3 dimensions. Accurate structural analysis requires shifting focus from two-dimensional cross-sections to volumetric microcomputed tomography data. In 3 dimensions, fibers do not run in perfectly straight lines. They exhibit continuous, wavy paths and out-of-plane misalignments along their longitudinal axis. Capturing complex 3-dimensional waviness requires massively scaled representative volume elements, containing thousands of individual undulating fibers. This introduces a severe computational bottleneck. Simulating thousands of wavy fibers using traditional 3-dimensional continuum finite elements takes days or even weeks of continuous processing time. To bypass this bottleneck, engineers employ shell beam kinematic modeling. A solid 3 are mathematically simplified into a 1-dimensional central beam, connected by flat 2-dimensional shell elements. The shell beam method maintains accuracy by using beams to calculate fiber bending and compression, while shell elements simulate the matrix shear, the specific mechanical interactions that drive real-world kinking. Replacing 3D elements with this model reduces simulation time by over 99%. Predicting real-world composite failure requires both the mathematical rigor to quantify microscopic chaos and the advanced computational kinematics to actually simulate it efficiently.